Internal coding of text. What is the meaning of internal coding of text? When we type A, the letter A, we see it as the A that we know, right? Capital A. But to the computer, it doesn't look like that. To the computer, it's a binary code, a binary number. So when the new computers came, there were several manufacturers and they manufactured the CPU according to different codes. Each computer had to have a code for A, B, C, 0, 1, 2, 3, like that. You had to have codes, but they didn't know what codes were used by the other manufacturer. They were secret. So they couldn't have a common one. It was okay. It was quite okay. It was going on until the internet became popular. When the internet became popular, when all the computers, different types of computers started communicating through the internet, the problem came. That they found that their languages are different. Like when one computer types A, the other one takes C, C, Z, P, or K. So that couldn't happen. Therefore, the American National Standard Institute, and there are various institutes like that, they formulated a standard code for every manufacturer, every computer. That was called ASCII, American Standard Code for Information Interchange. If you want to interchange information, then you have to have a same code, same language. So the need for unique binary code for each distinct individual component item of the text. What is the meaning of each distinct individual component? If you take this is one component, one, the dot, another component, 0, another component, 4, space, even the space, it's a component. So even for space, you need a code. The computer should know what is the space, what is the hash sign, what is the 0, what is capital A. They should know. And the computer will know only by these binary codes. So many such coding systems in the history of computing. As I told you, there were many, but they had to be uniform later on among the same code. So that was called ASCII code. ASCII code, character code. They used 7 bits of a byte. 7 bits of a byte. And now you know the total value, the number of values you can have with 7 bits is 128. Already you know we have done binary. So here is a part of the code. Some examples of ASCII code stored in 1 byte with the most significant bit set to 0. So the 1 byte, we don't use the most significant bit on this side. Bit number 7, that is starting from 0, bit 0, bit 1, bit 2, that's the way it goes. So that is not used. That's why 7 bits are used for the data. So some points to note here. A limited number of the codes represent non-printing or control characters. Data for data transmission also you need, because they come in a stream and the other computer doesn't know what type of, how many bytes, what is the beginning of a stream, what is the beginning, what is the end of a block, and those things. Because of that, you need control characters. And even for typing and printing, you will see that when you click this one in Word, not printing, non-printing character. These are control. End of the need a character code. The majority of the codes are for characters that would be found in an English text. So on the keyboard, you get all the alpha keys, that is alphabetic keys. Then you get the numeric keys. So those are called alphanumeric keys or characters. Then you get the punctuation marks. So on those characters, you have the upper and lowercase letters, that is capital A, capital B. Then the punctuation marks, linear digits, and arithmetic symbols, plus, minus, those are also there. The codes for numbers and for letters are in sequence. The codes for the uppercase letters differ from the codes for the corresponding lowercase letters only in the value of bit 5. So let's look at this. A, the binary code is this. Simple A, there was a mistake in the textbook, so I've corrected it. This is simple A, and it is this. What is the difference? Only in this bit. That's a bit 5. Bit 0, 1, 2, 3, 4, 5, started from bit 0. So only here, the capital letter there is 0, the simple letter is 1. All the rest of the byte is the same. Even B, to take, it's like this. Only that bit is different. So it's easy. The codes for numbers and for letters are in sequence. So they are in order. In sequence means for A, this, then B, one by one is going on. This value, what is this value? That is a hexadecimal value. This is a hexadecimal value. And you have the denary value as well. So the denary values, if you take, for capital A is 65, for simple A is 97. I would recommend that you remember this 65, at least 65 and 97, so that if you are required to write some word or something or a character in ASCII, it will be very easy. How do you do that? What is a ASCII character for? Zero, 1, 0, 0, 0, 0, 1. Is it 1, 2, 4, 8, 16, 32, 64, and this one 65. Binary value is 65. Supposing you want the K, you want the code for K. How do you do it? You start counting from B, right? B, C, D, E, F, G, H, I, J, K. Up to K, how many characters? So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what do you do? Then for K, it is 75. That is for K, 10, 10 plus 65. That 65 is from the original A, value of A, linear value. So then you will get, likewise, you can make any number, any word or something, and the code for binary code for 75, that's it. So at least 65 you remember. Generally they give for the exam, but better if you can remember that. Then there are 100 and, now how many codes are there? 128. Then in time to come, they found that 128 is not enough. You wanted to introduce more and more, like graphical characters and all that. Then what did they do? They extended the 7 bits to 8 bits. That was called extended ASCII code. So character code is 8 bits. 8 bits use total of 256 codes available. Then the most used standardized version is ISO Latin 1. That's the version. After some time, this 256, though it included English and a few other languages, the Japanese, Chinese, Arabic, those languages which had thousands of characters could not be included in 256. So they started using more than 1 byte, and it was called Unicode. Of course, the first byte remained the standard codes, which were already there. They did not have to change anything in the first byte. The most popular version of Unicode, which is discussed here, is named UTF-8. It uses more than 1 byte and it can accommodate all languages in the world. So that's a great achievement. So if the first byte is there, you know that that's a normal ASCII. Only 7 bits are used. This question mark is for the available bits. So then 7 bits means you had how many values? 128. When you're using 2 bytes, they didn't do 16. They didn't do 16, just like in ASCII, they left some bits for identification purposes. So if 2 bytes are used, there are 11 bits free. 5 here and 6 there, leaving 3 bits on the most significant byte here and 1, 0, 2 bits on this side. You will notice that all these subsequent bytes are 1, 0, starting from 1, 0. These are only different, the beginning, to identify the beginning code. So if 11 bits are free with these 2 bytes, it will allow 2 to the power 11, which is 2048 different codes. Unicode has its own special terminology and symbolism. A character code is referred to as a code point. So they are given in code points. In any documentation, a code point is identified by U plus followed by a 4-digit hexadecimal number. Like this, U plus. The code points U plus 00002 to U plus 00FF define characters which are a duplicate of those in the standard Latin 1 or extended ASCII. That means 00002 00FF means FF is 256. You convert this. This is hexadecimal. You convert this to denary. This will be 256. Which are a duplicate of those in the standard Latin 1 extended ASCII scheme. So those need not have been changed. Otherwise, there'll be a problem. The old coded signs were to be changed. If those codes to be changed, big problem. So they were not changed in the Unicode also, it's the same. The binary codes representing corresponding to U plus 00002 U plus 007F use 1 byte only and range from 000 through to this 771 bits. That means what? This is 0 to 256 and this is half of it. 7F is how much? 7 into 16 plus 15. Right? 7 into 7 into 7 into 16 plus 15 into 1. The following values, the following value of this is 60 to the power 1. Following value of this 60 to the power 0 is 1. So 15 into F is 15 in denary value, 15 into 1, and here 7 into 16. And you get the value. How much? 100 and how much? 12. 7 into 16, 42, 4, 12 plus 4, 11 plus 15, which is 127. It will become 128 plus the 0 code also. Using the 0 also, 0 to 127. So that's how you get 128 codes for half. And the balance is, how do you say balance? Then the binary code for u plus 0080 to u plus 00FF. We took 7F. What is the next number? In hexadecimal, what is the next number? In other words, 7F plus 1 is how much? Go to the counting. We did first day. There is no 7F, but let's take 1F. After 1F, what happens? It's 20. 1F, it's 20. If it is after 7F, what will happen? It's 80. No? So there is 8. 80 to the balance part of the full code 00FF. Require 2 bytes. Then you need 2 bytes and range from 110. Now see, is 110 is a from 0 for the first byte, followed by 10 here, 10, and the others 00 for the second byte. That is the first number starting from 0 through to 110. That is 110 0001, followed by 10. That is the second byte 10. This up to the full 1, 2, 3, 4, 5, 6 bits. So u plus 000 to u plus 007F. This is a kind of summary. 7F. That is using 1 byte. U0080 to u plus 00FF. This 11111111. That is F. This is the 7111 is 7 and F is that. And here it's 1111 is a F and here also F. And starting from 80. This is 8. This is 8. And this is 0. That's kind of summary. This is 8. 8 and 0 to 8 and F. Then we come to images. Vector graphics is one of the 2 forms that we are going to learn. The other type of image is bitmap. Bitmap images and vector graphics. So first we take vector graphic. Vector graphic file has a drawing list, which has a command for each object. Drawing list means the objects. There's a list of objects. Attributes. They have a which define a property which like the color, thickness, fill color, outline, those things are the properties, size and all that. Basic geometric data. There is basic geometric data also. For a circle, you need the you need the radius. For a circle, radius is enough. But then you don't know where to draw, so you have to give the center also by way of coordinates. So this is the difference. In vector graphics, these are called, they are considered as objects. And these objects have various attributes, properties. In addition, properties are defined such as thickness and style of a line. If there's a line, then you need the thickness, style, color, the color of a line, and the color that fills the shape. We'll see, we'll be doing that in detail. Before that, we just check the definitions. Vector graphic, a graphic consisting of drawing objects defined in a drawing list. And the drawing object is a component defined by geometric formulae and associated properties. You know what properties are, the color and all this attributes. Drawing list contains one set of values for each drawing object. And the property defines one aspect of the appearance of the drawing object. So here's a task for you. Construct a partial drawing list for the graphic shown in figure 1.05. Read this. You can take measurements from the image and use the bottom left corner of the box as the origin of a coordinate system. You can invent your own format for the drawing list. So here, this is the drawing or the image. And the coordinates are starting from 0, going this way, the columns 100, and this way, the rows 100. So you want to give the, if you are thinking of the head, the object, the circle, and center, you have to give 40 and 80. How do you give 40 and 80? Is it this way or that way or this way? We don't know. Let's check it out with a simple drawing package. How do we give the coordinates? So this is a simple drawing. And the size of the image is 819 by 891 pixels. You remember about the pixel is a picture element. You know that's the smallest identifiable unit in a picture. Pixel, picture element. Now can you see this moving the coordinates when I move the cursor? Two coordinates moving, changing. Now here it's 819 into 891. Similar figures, it's easy to remember. Now I'm going to crop this. And then it became 211 into 165. The size of this picture. Earlier, the whole screen was there. 211 by 165. And look at screen when it moves inside this frame. 32, 153. If I move left, what is moving is the column. Column. So the first coordinate is column. Columns are this way, no? This is the column, and this way is the rows, horizontal. So if you move from there to down, the second coordinate move. That means the row. So the first the column and then the row. That is how. Again, now I am moving the column. Column is the first coordinate. And row from there So this is the starting point is 0, 0, 0. Difficult to think the person there. Very difficult. You may be able to. Yeah, there 0 and 1. So from 0 to go down, that's the row. To go right, that's a column. So column first. Column first. No second. How do you remember this? How do you remember? This is in alphabet. C comes first. R is second. This is in alphabetical order. So C first, R second. So you can take it like that. So how do we give the coordinates here for the center of the head? Take the column first this way. So from here, 0 up to this point, the center. It's about 40, no, a little less than. This is the center. If it was there, then it's 50. So less than that, take it as 40. Then the column, the row from which row? This is the first row, this is the second row, like that it goes down there, about 20, no? Center is here. So half of that is about here, and then 20 is less than that. So 40, 20 is a place where the circle is centered. So 40, 80, then radius 10. So 10 pixels or whatever. Okay, is just an example, not accurate. So 10 to draw the circle. And fill, with what color are you going to fill this? Red. Then outline, what's the color? Blue. So blue outline. Let's complete that object. So your task is to complete this. And you can submit it. Then on the website, on your course web page, you have a place to submit this task 1505 and all other tasks. You have to do that. It's very important. I repeatedly tell you, very important that you do all the tasks. Otherwise, at the end of the course, you are going to the exam, you will find it difficult. On the other hand, if you do all these tasks, you will be very successful at the exam. The image is scalable. Whenever the image is to be displayed, the file is read. What do you mean by read? So here, if you increase this, you increase the size by the resizing, resize 100, you make it 200%. Because this starts showing, no? Early it was a smooth line, but here now it's ragged. The quality has gone down. The pixels are shown. These are the pixels. That is in a bitmap. This is a bitmap. They just stretching the screen, the image. Whereas in the vector graphic, it's not that. The file saves, the file has all these information that we make this list here. And every time you increase the size or decrease it, the file information is read, the appropriate calculations are made. Center will not change. Center will change according to the full range. Otherwise, if you take it that it just enlarging it here, making it double, then the radius will be 20. Radius will be 20, so that this will become double. And all the other calculations like this will overlap that. So according to scale, you have to enlarge the whole thing. So all that is read and the calculations are done and displayed on the screen. That is the difference. In a bitmap, it doesn't happen like that. It just expands, like stretches, like balloon. If you write something on a balloon and you blow it, it gets distorted, no, the letters and the drawing or anything. So the calculations are made and the objects are drawn to a suitable scale. This avoids image distortion. What we saw in the bitmap file, image distortion. A vector graphic file can only be displayed directly on a graph plotter. It is an expensive specialized piece of hardware. So graph plotter is not the plotter that we think of like a printer. This is a display to display the vector graphic. A vector graphic file can only be displayed directly on a graph plotter, which is an expensive specialized hardware. Other types of display, like the one that you and I have, the vector graphic file often has to be converted to a bitmap. So if you want to display a vector graphic file on our screens without buying that expensive piece of hardware, then that vector graphic file has to be converted to a bitmap file. Okay? And the vector graphic example file formats are SVG, WMF, EPS, PDF, CDR. PDF you already know. CDR is a CorelDRAW extension. And we come to bitmaps. Images which have no geometrically defined shapes are generally stored as bitmaps. They are not geometrically defined, like the circles and rectangles. They're just example scanned images or screenshots. If you take a screenshot or a scanned image, those are the ones. They are just bitmaps. The definition of the objects and all that is not there. Picture element, which is called pixel for short, is the smallest identifiable component of a bitmap image. The image is stored as a two-dimensional matrix of pixels. Matrix like a table. The pixel itself is a very simple construct. It has a position in the matrix and it has a color. So two-dimensional means there are two coordinates, not just one. When you do arrays, you know that uh, array is you just take one column of this. See whether there is one column once. Yeah. So I'll copy this. One dimensional array. So if you have 5, 6, 12, 85, 400, 56 data, and you have only one coordinate to refer to. Now, if you want, now if the name of this array is AR1. AR1, if you want the coordinates or the other value. Want to get is 50 or 100. Value 100, what do you do? Okay. R1 element number. 1, 2, 3, 4, 5, 6. That's the way, right? But if you uh, you have two dimensional. about that. Then if you want to refer to this, say 100 here, 50, 85, and here 40, 98. Right? If you want to refer to this 100, this is AR2. See, AR2, we have to give two coordinates, right? Two coordinates, and here, of course, the row first and column second. Huh? So there is a little bit of confusion there, but we will master it later. So this 50 will be one, row is 1, 2, 3, comma, column is 2. The two-dimensional doesn't mean that it's only two rows. It can be even another, right? We can have more than one for a two-dimensional row. Then the appropriate coordinate should be given. So in this case, here there are 3 columns, and this says the pixel itself is a very simple construct. It has a position in the matrix and it has a color. So what is the position of this 0? It's 1, 1, right? 1, 1. And what is the color? It's black. Or in its code, it's 0. If you are using 1 bit to define the color, you can use 1 bit to define the color of a pixel. So these are pixels. 3 pixels this way, 3 pixels this way. So altogether there are 9 pixels for this picture. And to define the color of a pixel, the simplest option is to use 1 bit to represent the color, so that the pixel is either black or white, 0, 1. So here all the zeros are 1, zeros are black, and the ones are white. So there is a thing called color depth. How are you going to remember this? Because there's another thing called bit depth. Not to confuse that. I will give a method to remember. Imagine each pixel is painted with bits. Each pixel painted with bits. So if you use 1 bit to paint, there's only 2 colors. Either 0 or 1 is 1 bit. So that is called the color depth. If you use 2 bits, you can have how many? 1, 2, 3, 4. 0, 0, 0, 1, 1, 0, and 1, 1. So with 2 bits, you can have 4 colors. Maybe that 0, 0 is black, but we have to define. We have to define what other colors. 0, 1 is dark gray, and 1, 0 is light gray. 1, 1 is white. So, and also 3 bits, you can have 8 colors. So how are you going to say, for example, quickly, if you want to check for 6 bits, how many colors? It's 2 to the power n. That's how it goes, 2 to the power n. If it is 6 bits, 2 to the power 6. So color depth, how are you going to remember? Like paint with bits, the color codes, you sometimes that you give the first coat, then the second coat, the coating of color. So that's called the color depth. How many bits? How many bits are used to describe this pixel? At least 8 bits per pixel are necessary to provide a sufficient range of colors to provide a reasonably realistic representation of any image. Now let's look into this in deep detail. If there are 3 bits, you can have how many colors defined? 1, 2, 3, 4, 5, 6, 7, 8. You don't have to count because 2 to the power 3 is 8. So if you take this one, the descent 000 is black and 111 is white, then how many other colors can be defined? 1, 2, 3, 4, 5, 6. 8 minus 2 is 6. So is 6 colors enough to have a natural image, natural picture, photograph or something? Not enough, no, because we need at least 7 colors, no, in the rainbow. Even if you don't, now here you get brown, the face, or something, you get various shades, no, various shades. You get hair, old people, different shades, starting from black, going on to white. So that's not enough. 3 bits not enough. This says at least 8 bits per pixel are necessary to provide a sufficient range of colors to provide a reasonably realistic representation of any image. So now 8 bits, how many colors? With 8 bits, how many colors are possible? That is 256. Now you must be an expert on the calculation of these bit values. So 8 bits will give you a total of 256 colors. So that will be realistic. No? When you take red, light red, dark red, and when you mix colors, you get many other shades. So 256 you can have. Here it's 6 colors. Even if you had 7 here, only one bit for one color means red is red, brown is brown. There is no shading of anything. So it doesn't look natural. So the number of bits per pixel is sometimes referred to as the color depth. So we learned that per pixel is color depth. Another term, bit depth, is the number of bits used to store each of the red, green, and blue primary colors in the RGB color scheme. You remember we did a web page and showed you how the colors can be changed using the hexadecimal values in the HTML file. So to take color depth and bit depth in this column, the number of columns here, the color depth is 8 bits per pixel, then 256 colors. If the color depth is 8, that's how it is said. If the color depth is 8 and the unit is bits, you get 256 colors. If the bit depth is 8, that is given per primary color, 8 bits per primary color, which means 256. And there are 3 colors, RGB. So 256 into 256 into 256, all the mixture of colors will give you 16 million plus colors. So that's a very good quality format. The key terms now: picture element, pixel, the smallest identifiable component of a bitmap image, defined by just 2 properties: its position in the bitmap matrix and its color. Color depth, the number of bits used to represent 1 pixel. Bit depth is the number of bits used to store each of the red, green, and blue primary colors in the RGB color scheme. If a lower bit depth is used, the image will show bands of color. It won't give a true picture, true color or natural picture. There'll be like bands showing. Then what is the resolution? The product of the number of pixels per row times the number of rows. So per row, how many? And how many rows? Which means number of columns and number of rows, no? Like calculating the area of a rectangle. So in this case, how many? What is the resolution of this? Each square is a pixel. So 4 pixels per row, in this case, into 4 rows, which means 16 pixels. And the unit is px. Very important to remember. Resolution is px, the pixels. Example file formats: JPG, PNG, APNG, GIF, WebP, BMP, and MPEG-4. There is a thing called spatial redundancy where it happens when a sequence of consecutive pixels in the same frame have the same value. So in this case, this one or three consecutive, or maybe if you're going wrap around, then four. 1, 2, 3, 4. For 4 bits of pixels, the same value is there. Same color value is there. That is called the spatial redundancy. Duplication. Consecutive pixels in the same frame have the same value. Same frame. There are frames, even video or whatever, like first frame, second frame, like that. So if the temporal redundancy is when a pixel in the same location in two consecutive frames has the same value. So the next frame, if this is one value and the next frame also is the same value, then that is called the temporal redundancy. And again, the definitions: bit depth. Bit depth, the number of bits used to represent each of the red, green, and blue colors. Image resolution, the number of pixels in the bitmap, defined as the product of the width and the height values. Screen resolution, the product of width and height values for the number of pixels that the screen can display. So this, to take this one, the resolution of this is the number of bits this way, number of pixels, this way, and number of pixels down, multiply. But screen resolution is the full screen. How much can the full screen display? The product of width and height values for the number of pixels that the screen can display. So image resolution and screen resolution is different. What is the difference between color depth and bit depth? So pause the video if you like and then think about it. Can you answer that question without getting confused or getting mixed up with the two definitions? Here is a worked example. You have been asked to calculate a value for the minimum size of a bitmap file. The bitmap is to use a bit depth of 8. See, terms that you learn are coming. Bit depth of 8, and the bitmap is to be printed with 72 dpi, means dots per inch. Usually printing, that's the way it is given. And to have dimensions 5 inches by 3 inches. 5 inches by 3 inches. So the dots per inch is 72. 72. And then the dimensions of the picture is 5 by 3. We use the information provided about the color depth of the bit depth or the bit depth to give the number of bits per pixel. In this case, the bit depth is 8. Given here, the bitmap is to use a bit depth of 8. So, which means 8 bits for each of the RGB components. Remember, not color depth, the bit depth. So 24 bits are needed for 1 pixel. That means 3 bytes. Let's state that 72 dpi means 72 pixels per inch. So we'll just approximate it like 72 dots per inch is equal to 72 pixels per inch. So the number of pixels per row is 5 into 72. Why 5? 72 is given. Actually, 5 is also given. 5 inches. So the column this way 5, 360. And the number of pixels per column is 3 inches. 3 into 70, 216. Therefore, the total number of pixels is 360 into 216 equals 77,760. At this point, I must tell you that you don't have to give final answers, final results of the calculation. You can just say uh, 216 to 360. 360. That would do. Then, because you are not supposed to take calculators for the exam and you can't be doing these things on paper, it will take time. The total number of bits is this value multiplied by 24. Right? 24. So if you do the calculation into 24. So this is up to this point. Is what? It is pixels. When it is pixels. That is because there is the resolution. And here it becomes what? Bits. Then it becomes bits. So it becomes a size. Thereafter, what happens? Then, if you want to, now this is in bits, you want to convert it into bytes, by 8. Then the unit is bytes. And thereafter, you want to convert it into kilobytes. By 1000. Want to convert it into kilobytes. How much? Divided by 1024 will be. See what happens in the book. The total number of bits is this value multiplied by 24. However, we want the size in bytes, not bits. So we multiply by 3 because there are 8 bits in a byte. So this 24 divided by 8 is so it can be written as same as instead of this what divided by multiply by 3, you know, 316 to 216 multiply by 24 divided by 8 means multiply by 3 in simple terms. Okay, that is what they have done in the book, and you also can follow that pattern so that you can save time. But must be quick. Otherwise, if you go to divide 24 by 8 and it comes 3, no, at once, when you say 24 bits, you must know that is 3 bytes and then divide, multiply by 3 to get the bytes straight away. So one step is skipped. Bypass one skip going into bits, straight away bytes. We can code this in kilobytes by dividing by 1024. So difficult to get the final answer like this, 227 GB, 8 GB, but you can give the answer like this. That's enough. Because in some mark scheme, they have shown like that. So file header, a set of bytes at the beginning of a bitmap, which identifies the file and contains information about the coding used. So how is the coding used? It has to be coded, no? The image. So it defines so that the computer can understand what type of thing is this, an image, and how should I draw it. The images are finished. Now we are coming to sound. Sound contains a large number of individual waves, each with a defined frequency. The result is a waveform in which the amplitude of the sound varies in a continuous but irregular pattern. I'm sure you know the meanings of these waves, frequency, then the amplitude of the sound varies, irregular pattern. All these things I'm sure you have learned in science or physics. So original analog sound signal has to be converted to a binary code. What does that mean? Original analog sound. When we talk, when the sound comes, it's not analog, it's a sound wave. But when we capture through a mic, you talk to a mic and then capture, then what happens? Signal is generated by the mic so that can be either amplified and given, played over the loudspeakers or recorded, captured the hard disk for sampling later. So when that produces this signal, it's not a digital signal that is produced, it's an analog signal. But the computer doesn't understand analog. So the measured sound values are put into a sound encoder which has two components. So you have to encode what is recorded, the sound recorded, you have to convert it into codes, binary codes. That's called the encode. So which has two components. The sound encoder has two components. One is band limiting filter, which removes high frequency components which the human ears cannot detect. You already know the sound range, frequency range that the humans can hear. Dogs can hear more, the high-pitched songs and all that dogs can hear. So, but just because we don't hear, it doesn't mean that the mic doesn't hear. Mic gets all that and then converts it. So, but why do you remove it? Why do you want to remove it if you don't hear it? Because though we don't hear it, when the microphone hears it and then stores on the hard disk, that part also is information. But we can't hear also needs bytes to store that part. So that's not important. If we can't hear, what's the point? Just getting the file getting bigger. So we limit that. It's called band limiting filter. That is also done by the encoder. The second function is ADC, which means analog to digital converter. In control systems, when we do control systems, you will learn about sensors which produce analog signals and they have to be converted using an ADC so that the processor can process it. Let's look at how this is happening. Sampling operation of the ADC. This is the amplitude of the wave, the red line here, has to be completed at, has to be sampled at regular intervals. Sample means you have to, now this is the wave is going, now we have to record this. No? You have to record this to keep as a file. The blue vertical lines indicate the sampling times. So you can, if you can take a recording here and the next recording, if it is here, you have missed all in between. No? It's not a good recording. So you have to take closer. At regular intervals, you have to take recording. Sample at regular intervals. The blue vertical lines indicate the sampling time. So you take one here, when the wave is moving, another one here, another one here, another one here, like that. 7 samples are being taken here, going on to the 8th here. The amplitude cannot be measured exactly. Instead, the amplitude is approximated. The circle, this one, sample values 1 and 4, this and this, will be an accurate estimate of the actual amplitude. That means it will be 0, 0, 0, and this one will be 0, 0, 1. Because it's touching this line, touching the amplitude line, the measurement line. But the blue one, the samples 5 and 6 will not be accurate. Why? This 5 is it 011 or 100? In between, no? This is touching the line in between. Even this is like that, not a correct exact line. So they are to be what you call approximated. To code sound, we need to make two decisions. Sampling resolution. One is sampling resolution. Number of bits we will use to store the amplitude values. If we use 3 bits, 8 levels can be defined. That is 001 going up to 111. So let's have a look at this diagram again. So the numbers have not come. So 0 to 111 is like this. And if too few are used, that means few bits, like less than, like even three, what happens? There will be a significant error. Significant error, because these will be error. So this will not give a correct uh, reproduction of the sound. And what is a reasonable number? 16 bits. 16 bits provide reasonable accuracy, which means for 3, it's can go up to 7 points, 7 lines like this. The accuracy increases with, if it is 4, then you have 16, 2 to the power of 4 is 16. So it goes even more. In detail, you get. So 16 bits is the reasonable one, reasonable accuracy. So very accurate, because you can get, this half here. This half here and half there will not happen. It will be, because these will be very close. These lines will be very close to each other when you have 16 bits, and very, very close, so that it will touch some line. There is a chance that it will touch one line somehow. So it will be accurate. Sampling rate, that's the other one. It's easy. Number of samples taken per second. So here in this case, 7. If it is 1 second here, is 1 second for this whole range, it will be 7, the sampling rate. That is not bits or anything, but the number of samples taken per second. It's easy. Number of samples taken per second. 1 here, 1 there, like that, 7. An increased sampling rate and an increased sampling resolution will both cause an increase in file size. So its advantages to get high quality the sound resolution and sound reproduction, to use more bits. But then what happens is the file size will increase. So analog data obtained by measurement of a physical property, which can have any value from a continuous range of values. These are sensors. In other words, these are sensors. control systems, like in greenhouses and all that, you get these things, and they a physical property. They measure a physical property from the outside world, like heat, the temperatures, light, humidity, pH. All those values can be sensed by the sensors, and they produce analog. That's the problem. Analog signals. And digital data, data that has been stored as a binary value, which can have one of a discrete range of values. Unlike the analog, here it's discrete. Somehow you get some value there. Sampling, taking measurements at regular intervals and storing the value. The sampling resolution is the number of bits used to store each sample. Remember the image resolution? That's also called color depth. Number of bits used to store each pixel. And the bit depth is number of bits used to describe each primary color. So sampling rate now, EC, the number of samples taken per second. Compression techniques. Why do you want compression? Large files require large storage capacity and lower transmission or download rates, because there's a problem when the files are large. Two categories of compression. One is lossless, the other one is lossy. In the lossless compression, file size is reduced, but no information is lost. Process can be reversed to recreate the original file. So you can get the original one if you want. But lossy compression, file size is reduced with some loss of information, and the exact original file can never be recovered. Combination of lossless and lossy methods also can be used. The lossy you can't recreate for any reason. If you want the original file, you can't. So the key terms, lossless compression is coding techniques that allow subsequent decoding to recreate exactly the original file. Lossy compression, coding techniques that cause some information to be lost so that the exact original file cannot be recovered in subsequent decoding. Most compression techniques have been developed to work with a particular type of file. So here is one, run length encoding. It works particularly well with a bitmap file. Converts sequences of the same byte value into a code that defines the byte value and the number of times it is repeated. So for example, there are 4 bytes here. We'll see that there are 4 bytes. This is one, this is another. And the value also is the same. We'll notice the value is the same. So these 4 bytes can be encoded 2 bytes. How? 4 into this byte. This is a byte value, the exact byte value there. And this is the number. So 1 to 4. This 100 is 4. So this can be 2 bytes. So reduced by 50%. If you had 6 bytes here, 6 bytes here, then what happens? Still 2 bytes. So the same byte value here by 6 will be 110. 110, which is 6. It's a very simple technique. Then there is a thing called Huffman coding for text files. That is ideal for text. Each character is given a code. And these codes don't, none of the codes begins with the sequence of bits representing a shorter code. So this 10 will not start with any other code. 01, no. 111, no. So therefore it is unique. And then for the alphabet it's given. So you can use that. Huffman code can also be used for compressing a sound file. This is effective because some value for the amplitude occurs far more often than others do. So the more repetition, the better, the more effective. Otherwise, there is no use. For example, if we take this again, the earlier one also, it's the same. More repetition is better. Suppose if these 4 bytes are different, right? These 4 bytes different to each other. Then what? For each byte, we need 2 bytes. Here it will be 1 and the byte value. Another one, 1 byte value, 1 byte value. So it will be 8 bytes. So it goes the other way around. The purpose is lost. 4 bytes to be encoded with 8 bytes. That kills the purpose. So there is no point in that. Lossy compression can be used in circumstances where a sound file or an image file can have some of the detailed coding removed or modified. This can happen when it is likely that the human ear or eye will hardly notice any difference. One method for lossy compression of a sound file takes advantage of the fact that the successive sample values are unlikely to change very much. That's another one, apart from the earlier things that we said. So let's take an example of how bits are used to describe a picture. If you take a picture, camera will take the picture, and we don't see some rays. What are they? We see the 7 colors, but do we see infrared and ultraviolet? We don't see. But the camera sees. You look at this. This is a remote control I have, remote control. And when you press, though you can see from this side, this doesn't show, but yeah, when you, this side you will see, the human eye you can see. You take your remote control at home and then try to do this. You look at this, you see something when you press from this end where you point at the TV. But if you do it like this, you won't see. With the human eye, it's not visible. So what happens? That is infrared. By the way, the TV remote control uses infrared. So that part also is stored. There is infrared, for heat and all that, you get infrared. We don't see it. But that is also taken and stored. But what's the use? We don't see. Bits are used by bits and bytes. So because of that, you take it out. But when you want to, in case you want to get the original, you can't. That is a difference. Lossy. For a bitmap, a simple lossy compression technique is to establish a coding scheme with reduced color depth. Now, remember what you learned, color depth. If you reduce the color depth, the file size reduces. Then for each pixel in the original bitmap, the code is changed to the one in the new scheme, which represents the closest color. Right, so that is the end of chapter 1.